So for Adopt a Climate Station number 5, I had a couple questions, and I thought it would be useful to clarify it by creating a little video here. Um, the gist of assignment number 5 here is to do some sort of investigative work into the root causes or sort of teleconnections associated with anomalous climate conditions for your station. And by anomalous climate conditions, what I'm specifically referring to in this assignment is really the time period between January and April. So this is basically late winter, early spring. So again, we're looking at the time period January through April, not necessarily January, February, not necessarily each individual month. So what you're supposed to do here is basically look at your data, look at your station data, and I want you to select out the top 5 warmest January through Aprils, the top 5 coldest January through Aprils, the top 5 wettest January through Aprils, and the top 5 driest January through Aprils. Now, one question you might have is whether you want to do this, whether you actually want to pick out the top 5, warmest, coldest, wettest, driest over the entire period of record, or just for, say, the last 30 years. And I'm going to leave that up to you in terms of deciding. We're not going to be necessarily grading based on whether you select the right years or not. I'm going to leave that up to you. However, I will say that you don't want to choose any years that were before 1948, because the data set that you're going to be looking at here through the web page only goes back to 1948. So anyways, go through your data, pick out the top 5 warmest, coldest, wettest, driest January through Aprils. Okay, report that. Just jot down the years. Okay, you might want to put that into a spreadsheet, and maybe also, for your own sort of purposes, figure out what the sort of temperature anomalies were for those time periods. Sort of what sort of percent of normal precipitation relative to the 1981 to 2010 period that you saw for your wettest and driest periods. Okay. And the idea here is then to go and use the Earth System Research Laboratory's nice sort of web page interface, and you're going to be looking at a couple different ways in picking out the large-scale sort of top-down climate drivers associated with cold, warm, wet, and dry periods for your station. Okay. So what I'm asking here is that you go to the web page, okay, and you're going to be looking at a few different variables. And those variables include things like the geopotential height field at 500 millibars or hectopascal. And again, recall, going back to our discussion on climate dynamics, that this is giving us a good indication of sort of the placements, okay, and also the sort of intensity of large-scale troughs and ridges in the atmosphere. These are these large-scale waves in the atmosphere. All right, and just again, do recall that basically where we have troughs in the atmosphere or anomalously low heights, that corresponds to both sort of cooler than normal temperatures through the atmospheric column, and it also corresponds to more cyclonic or sort of stormy conditions. We didn't necessarily go into talking about vorticity much, but when we have sort of troughs in the atmosphere, that tends to coincide with synoptic disturbances, and that's when we tend to see our stormy weather. The other factors you're going to be looking at, the vector wind at 250 millibars or hectopascal, that's giving us an idea of the placement and intensity of the jet stream. Okay, mean sea level pressure. Okay, and mean sea level pressure is also going to tell us something about surface high pressures and low pressures. This factor here will not necessarily be associated with temperature. Okay, and one reason for that is in mid-latitudes, there's no sort of prerequisite such that high sea level pressure always needs to be associated with cold temperatures. And in fact, what happens typically in mid-latitudes is that we have something called a barotropic atmosphere, meaning that low pressure at the surface often coincides with low pressure aloft. So when we have sort of disturbances come through, storm systems come through, we see drops in both the geopotential height field, we see a trough, and we also tend to see surface low pressure. So that's very different than the sort of Hadley circulation type features that we've talked about with the general circulation. Other factors here: total column precipitable water. This is basically how much moisture you have in the atmosphere. If you were to take sort of all the moisture from the surface to the top of the atmosphere, condense it out, and measure it in a rain gauge, for example, that's how much water you would have in the atmosphere. So a more moist atmosphere you might expect to be correlated with, a wetter January through April for your area. And then finally, the last feature here to look at is sea surface temperature anomalies. Okay, and again, sea surface temperature anomalies might give you some information to link factors like El Nino or other sort of climate modes, low frequency climate modes, to wet, dry, warm, cold January through April's at your site. Okay, so let me just walk you through how you might go through this. And again, you're going to be looking at these sort of patterns for the 4 different cases that we talked about. And I want you to sort of come up with a sort of, a brief description connecting all these features together. And you're basically trying to come up with a formula or ingredient list, if you will, for having a cold, warm, dry, or wet January through April at your station. Okay, so you're going to do some generalizations, but I'm asking you to do that, so don't feel too bad about it. And let's go through one example here. I'm going to be looking at specifically the 500 millibar geopotential height, and I'm going to go to the page here. So this is the page, and let me zoom in just a bit here so we can kind of see what this looks like. Okay, so which variable we're going to choose, and I told you 500 millibar geopotential height, so let's choose here 500 millibars. Okay, this is halfway through the atmosphere. The beginning month of the season, we're looking at this from January through April, so choose January through April. Okay, and it says enter the years for composites. Okay, and I'm just going to choose a set of random years. Actually, yeah, I'm just going to choose a set of random years here. And I'm going to choose only 2 years. You're going to be actually kind of compositing on 5 years, as I told you. But let me just choose 2, and you can extrapolate from that. The 2 years I'm going to choose here are 1983 and 1998. Okay, and you could keep going on, but you want to enter your 5 years here. So if you found the 5 warmest years, you'd enter them all here. Okay, and a composite basically takes the average over those 5 years. Okay, so scroll down here, and the type of comparison that I want to plot, I think I should just leave that as is. You could choose anomaly here, but I think if you choose anomaly down here, where it says plot type, and you select anomaly, that should do the trick for you. I don't want to change any of these other features here. I think I can leave it as is. The map projection area, most people are probably choosing places in the western United States, so we could choose the PNA region, Pacific North American region. I believe that's what I told you to do on the web page here. However, one thing that I think you probably should do is when you do sea surface temperatures, I'm going to suggest that you choose the global projection so you see the entire globe, because it's very much possible that your teleconnection patterns for years that couple to sea surface temperatures might involve sea surface temperatures in the tropics, and so you'll see this region here does not necessarily include all of the tropics. If you choose your map projection as such, you can leave it just like that. Okay, and I think at this point you can say create plot, and we'll see if this works. Okay, so we have a field that came through. Okay, and it'll tell you here this is the 500 millibar height field composite anomaly from that same time period that I told you that you wanted to take anomalies for. So this is nice. This does it for you. Okay, and again, January through April, the years 1983 and 1998. Okay, so now what we see here, these are the anomalies in terms of 500 millibar geopotential height. Very, very strong negative height anomalies across the Northeast Pacific Basin, across actually much of the United States by and large. Okay, and so just for all intents and purposes here, a negative geopotential height anomaly means that height fields are decreased quite a bit in this area. Okay, and what you'll also notice here is that positive geopotential height anomalies mean that sort of temperature in the lower column of the atmosphere are increased. And so what you see here is this significant decrease in height anomalies across the Northeast Pacific and an increase in height anomalies across the sort of subtropical Eastern Pacific. So increased height, decreased height, actually what that's going to mean is that you have a stronger gradient in height and probably a stronger jet stream across the eastern North Pacific during these years. And you probably should start to make that connection. A stronger gradient in height fields probably translates into a stronger jet stream, and that translates into a redirection of storm tracks across the entire Pacific Basin and into the southern tier of the United States. Okay, and you can actually just go back. So say if we wanted to change that now to look at the vector wind field, we choose vector wind, 250 millibars. I think that's what I told you to do. Okay, and then anomalies, and what we probably will see here is exactly what I thought we would see. So here we're looking at anomalies. These are departures from normal, and what we're looking at here is a significant intensification of the subtropical jet stream across the Pacific Basin and across sort of, actually the southern part of North America. Okay, so you're basically going to try to connect these features together. If it is useful to you, one thing that you might want to do, anomalies, may be a little bit challenging to look at, and so it might help you to, instead of looking at anomalies, go to mean here. So plot type mean, and these are the actual composite of the wind speeds rather than the composite of the wind speeds minus the sort of climatology or what we expect. So if I do this for these 2 years and I look at the jet stream, here is the jet stream, and we can see it's quite strong across the entire Pacific, and it stays quite strong, even going into sort of Mexico across the southern part of the United States. And so these 2 years I picked out were two of the strongest El Nino years in the past 100 years. And this is a very sort of canonical or obvious signature of how El Nino manifests itself in the extratropics. Okay, so I think you try that out for your stations. Again, don't do it for each individual year in terms of looking at the 5 warmest years individually, composite them together, and so you should start to make a set of plots. Basically, here I'm asking for 1, 2, 3, 4, 5. Basically five plots for each of the different warm, cool, wet, dry cases. So it's quite a few plots. I want you to connect them together and try to make these relationships between what's happening at 500 millibars, what's happening at 250 millibars, sea level pressure, precipitable water, and sea surface temperature.